Welcome to a new video. In this video we will discuss the Gram-Schmidt process. Gram-Schmidt process is a very simple method for constructing an orthogonal or orthonormal basis for any subsystem in the real plane. And this method also will lead us to one of the important factorization, which is called the QR factorization. So we will see, of course, our calculations in this example step by step, and also verify this in a MATLAB command window. Okay, before we jump to the actual Gram-Schmidt process, I will discuss briefly what a projection is. So if you have two vectors, let's say u and v, and they are in this space, and they are not equal to each other, then the projection of the vector v onto the vector u is called the projection vector p, which is then given by this symbol. And it's defined by this expression. You see here now the dot product of the u and the v divided by the dot product of the u with itself times the vector u. And this is now the projection of that vector v onto the vector u. Now we need to see that also graphically. This is of course what we can calculate, but how does it look like in a graphical form? So for instance, if you have an xy plane or x1 and x2, so two-dimensional problem, let's say we have one vector which is u, this red arrow, another one is the blue one, which is our vector v. Now we like to know what then the projection is of this v onto the vector u. That means actually you go perpendicular to this vector u, so you actually make now the shadow here. That shadow is this green arrow, and now we would like to know how do we calculate this length of this vector v onto this vector u. And this is now called p in this case, which is then given by this expression. Let's give an example. So numerical example, let's say we have two vectors u and v, which is given by 4 and 2 and 1, 3. So two-dimensional problem. We will calculate the projection of the vector v onto the vector u. We will use in our solution this definition. So it says the following. So in order to go from the vector v onto the vector u, you use the vector u with the dot product with the vector v. So that is actually shown here. So you do 4, 2, 1, 3. Now the dot product operation goes like 4 times 1 plus 2 times 3. And that will add up to 10 because this is 4 and this is 6. And we also need to do u times u. That means then 4, 2 and 4, 2. That will be then 4 times 4 plus 2 times 2, which is then 20. So it will be then 16 plus 4. Now we need to substitute that in here, and we have also our u here, so that will be then 10 over 20 or 1 over 2 times this 4, 2. That will be then, in this case, effectively 2, 1. So a new vector p, which will have then the x coordinate 2 and the y coordinate 1, which is then this projection of this vector v onto vector u. Okay, let's also see now the definition, so we get closer to the Gram-Schmidt process. So what is the definition of the Gram-Schmidt? Now let's say we have a basis given by this set of vectors, so x1, x2 up to xk, and that is forming a basis in a subspace which is non-zero in this space. And that subspace is called W. So then we can define, according to the Gram-Schmidt process, that we need to make v1, which is a new vector. We define that and set it to the first vector we have there, which is then x1. And a v2, which is the next vector, will be then orthogonal to this v2, will be then given by x2, which we have from our set, minus this equation we have seen in the previous discussion about the projection. So this is the projection we need to subtract from the second vector in order to go to the orthogonal vector, which is then the v2. Now this process continues. If you go to the v3, then you need to subtract also the other parameters, so you actually see this here also. And then you can do it in general form like so. So you go actually with subtracting all the projections for each part of the vectors. Of course, we need to see that also in action, and then when we are done, we can create here the v1, v2 up to vk, which is then now an orthogonal basis for the subspace W. Okay, let's see an example, because that is really helpful to clarify this process of Gram-Schmidt. So we have now again here two vectors in 2D, different vectors, x1 and x2, and we'd like to apply this Gram-Schmidt process to obtain an orthogonal basis, because this is not orthogonal. You can also check that by doing the dot product of x1 times x2. You see 2 times 1 plus 1 times 1 will be 3, so you need to come up to a 0. That is actually when you have a dot product of two vectors, that means they are perpendicular or orthogonal. In this case we don't have it, so how do we find now the orthogonal basis? Okay, let's now carry out the definition. Step 1 is we set this v1 to this vector x1, that is just 2, 1. That's just first step. Now the second step is calculate now the vector v2, which is the new vector, which is then given by this expression we have seen. Now we need to again do here the dot product v1 and the x2, and another dot product of v1 and v2, v1 and v1 I mean. And then you multiply that by the v1 vector, and then you need to subtract this from the x2. So let's first calculate this dot product. That's shown here. So 2, 1, 1, 1. That will be 2 times 1 plus 1 times 1. That is then 3. The next one is v1 and v1. The dot product of that one. Now 2, 1, 2, 1. That will be then just 2 times 2 plus 1 times 1, which is 5. Now we have now the sufficient information. We can now say it is 3 over 5 times this vector v1, which is this 2, 1 from step 1. And now we have here 1, 1, which is x2, minus 0.6 times 2, 1. And that will add up to minus 1 over 5 and 2 over 5. Now we have now our vector. We can now say, let's check this. Now these vectors v1 and v2 form now an orthogonal basis in the 2D space. But let's check this. This is always helpful to see that this is indeed correct. So we can say, let's check this. This needs to be a 0. Then the v1 and v2 are indeed perpendicular or orthogonal. So we have the v1, which is our 2, 1, and v2, which is calculated. So if I now work this out, 2 times minus 1 over 5 plus 1 times 2 over 5, which is of course 0. So we say this v1 and v2 are indeed orthogonal, and that means we have formed a basis in 2D. Okay, let's also see that in MATLAB. Now you can create a vector like so, so v1, and then you create it like so using a semicolon. So we have now 2, 1. Then another vector v2, which is calculated here, which is then this. So we define another vector v2. And now we need to see that this is the dot product, if this is indeed correct, which is indeed the correct result because we want to have a 0. So the calculation of the dot product of the vectors v1 and v2 is indeed 0. And that is also given here, so we say our calculation is indeed correct. Okay, now let's go to another example in the 3D, so in the 3-dimensional. So we have now 3 vectors x1, x2, and x3, and then we need to again apply the Gram-Schmidt process to obtain an orthogonal basis. You can see for yourself that this is indeed not an orthogonal basis. They are of course independent, but they are not orthogonal. Okay, so what do? In the calculation, step 1 is we define again or set the v1 is equal to the x1. So just that's really the easiest step. So you just make this v1, that's shown here. The next one is the v2. So v2 means x2 minus the projection of this matrix here, I mean the vector here onto this x1. So this is actually shown here. And now we need to calculate also this one. So how do we calculate that? Now we do again the dot product here, another dot product there. So let's do that here separately. So v1 and x2 dot product, that is then 1 times 2 plus 1 times 1 plus 1 times 3. That will add up to 6 because it's 2 plus 1 plus 3. The other one, v1 dot product with v1 itself. So this is again very simple, 1 times 1 plus 1 times 1 plus 1 times 1, which is 1 plus 1 plus 1 is 3. Now we need to substitute in here, so 6 over 3, which is then 2 times this vector v1. Now we need to do x2 minus this, which is then given here, and that will result in 0, minus 1, and 1. Now you can already check that the v1 and the v2 are orthogonal. You can just multiply this out. You can see that this is indeed 0, so the dot product of the v1 and v2. But we need to go to a third vector v3 because we have a 3D problem here, And that is then given by this expression. Now you see here an additional subtraction in order to go to the third vector. So you do now x3 minus the v1 times this operation, and now the v2 times this operation. So you see actually now as a template that where we have v1, you also have v1 here, v1 and v1. When you have v2 here, you have a v2, v2, v2 here, and there is also x2, x3 here, x3 here, and x3 here. So this is kind of a simple template you can use if you move on to the next vectors. Now let's again calculate the dot products. We need to first calculate this, which is v1 and the x3. We have it here, v1, we have here x3, which is from our example. Now we do have 1 times 1 plus 1 times 2 plus 1 times 6, which is here exactly 9. Now v2 and the x3, which is this one, that is then 0, minus 1 and 1, which is from the second step. And times, the dot product with the x3 here, and that will result in 4. Now v2 with the dot product of v2, that is the final one we need to know, because v1 with the v1 we already have calculated here. Now that is just the v2 here and the dot product with itself. So we have here now 0, minus 1 times minus 1, which is then plus 1, plus 1 here also, so you get exactly 2. Now this is now the result here. Now we can simplify this by doing 3 times these 3 values and 2 times these 3 values in the vector. Now we need to do the vector subtraction, so 1 minus 3 minus 0, that will then add up to minus 2, 2 minus 3 minus minus 2, which is then 1, 6 minus 3 minus 2, it will be then 1. So you actually go in the row subtraction. So we have our v3 also. So we have now the v1, v2 and v3, which form an orthogonal basis in this 3D. Okay, now let's check this. We need to make 3 checks. That is then v1 dot product with v2. So we see that this is indeed 0, because this is 1 times 0 plus 1 times minus 1, which is then minus 1, and 1 times 1 is plus 1, so we will add up to 0. The next one is v1 with the dot product with v3. We see here 1 times minus 2, which is minus 2, plus 1, which is also 0, so this is also correct. And then the final one, v2 with the dot product with v3, is here 0, minus 1, plus 1, and this is also 0. So we have now checked the 3 calculations here, and we can say that this is also valid in MATLAB by checking that here in the command window. v1, v2, and v3. We have defined it as we have calculated here. And this is now the dot operation of v1 and v2. And this is the dot operation of v1 and v3. And the dot operation of v2 and v3. So let's see what we have. This is 0 indeed, as we have calculated according to here. This is from the MATLAB here, also as we have calculated, and this is from MATLAB as we have calculated. So everything is correct. So we have verified our result also here using the MATLAB command window. All right, this was our example considering the Gram-Schmidt process to create an orthogonal basis. First, we have discussed the projection of a vector on another vector, and then we carry out our calculations in the Gram-Schmidt process and use this projection formula to come up to an orthogonal basis. See you next time in another video.